So now it's time for us to look at neutralization. So this is a neutralization curve, and we can draw one of these when we add either an acid to a base or a base to an acid in a titration. So what's really important here is to look at what's on the axes of this graph. Now the volume of the titrant added, now that's what's coming out of the burette at the top. That goes on the x-axis because that's the independent variable. That's what is basically you're changing. And what is changing as a result is the pH of the analyte. So that goes on the y-axis as the dependent variable. Now what you can see on the y-axis, the pH of the solution with acidic at the bottom and alkali at the top. Now with this particular example, you can see it's sodium hydroxide in the titrant. And to start, there's none of that sodium hydroxide in the analyte, which is a weak acid. And so what you can see is that if you follow the line, that the pH of the solution gradually increases until it gets to near the neutral point, the neutralization point, when it suddenly goes through this vertical section of the graph. And midway through, there's this equivalence point where basically you have as many H plus ions as OH minus ions. This is the point of neutralization. Then, when you go past that point, the pH continues to increase as you add more and more base. And what you find is, as the pH scale becomes less and less sensitive to small increases in concentration, remembering, of course, it's a logarithmic scale, that you have to then add quite a lot of the titrant to make any observable change in the pH. Now, these graphs can look different depending on exactly the situation. So let's have a look at some examples. But first things first, we must make sure that we're using the right vocabulary to describe the different parts of this graph. You see the almost horizontal, the flat starting part, we're going to call where there is an excess acid. You can see that's A on this diagram here. Now this is when we're slowly adding the base and it is not particularly changing the pH very much. And then it goes through B, the vertical section, where they are of similar concentrations and there is a rapid change in pH. And then we get to section C, where there is an excess of the base. Now the center of the vertical section is known as the equivalence point. And as we just said, this is where the concentration of H plus ions is equal to the concentration of the hydroxide ions. Now we can choose whether or not we have acid or base as the analyte. So you could add base to an acid or you could add an acid to a base. It is your choice, but it will make the graph look different. And because of the pH scale, it's really important that we've made a good observation of what is being added and what that's doing to the numbers in the pH scale. It's very easy to describe the pH increasing when actually we mean that the substance has become more acidic. So we have to then describe that the pH is decreasing. So sometimes people have a bit of a glitch where they think that more acidic means your pH is increasing. No. Just observe it carefully. The diagram on the left here is something that is starting acid and is becoming more basic. Now that means that the acid must be the analyte in the conical flask at the bottom, and we must be adding to it a basic substance, so in this case like sodium hydroxide or something like that. Now the other graph is starting basic and is becoming more acidic as it goes on. That means that it must be a base that is the analyte and we're adding to it an acid. Now a very good question is, how do we measure this? Well, we can measure it with a pH meter. If we put a pH meter in here, it will read off by detecting those H plus ions exactly what the pH is of the solution. And we normally have that in the analyte. As we are adding more and more of the titrant, the pH meter is telling us what the pH of the analyte is. Understanding a little about this equivalence point enables us to understand a little bit about some of the standard indicators that we use to tell us what pH a solution is. One that you might have seen is methyl orange, and it's this rather long molecule. But what you notice is it is a weak acid and a conjugate base, depending on whether or not that H plus ion is engaged with the the O minus ion at the very top. You see, if those two are bonded, then we get a red substance, and it's slightly basic. It's a conjugate base. If the H plus is dissociated, then it becomes an ion, and it actually physically changes the color of the chemical at that point. There is a difference in the absorption of white light to make it go from red to yellow, with a slight excess now of, well, a slight dissociation, I should say, of the H plus ions that have separated. Now we can go into a little bit more detail here, and we can describe how that color change comes about due to the positioning of the equilibrium. So if we were to add hydroxide ions to an acid, as in this example here, what we could see is they would cancel out some of the H plus in the indicator. And as it happens, it would basically turn it into water. And so it would neutralize the weak acid of the indicator. Now, this makes the weak acid itself dissociate more because the equilibrium has been shifted to the right. That taking out the H plus ions would mean that more would dissociate from the weak acid into solution. And this makes the indicator go from red to orange to yellow. Adding more acid has the opposite effect. It creates an excess of H plus, and that favors the reaction to the left. It moves the position of the equilibrium, meaning that we see more neutralization, and the methyl orange goes yellow, orange, and then back to red again. What about the acid dissociation constant of these indicators then? If they are weak acids, then maybe they have a Ka that is somehow linked to the endpoint of this neutralization. Well, at that point, what we find is the concentration of the undissociated acid would be the same as the concentration of the conjugate base, A minus. And for that reason, it enables us to rewrite the equation for the acid dissociation constant, Ka. Now, bear in mind that Ka is the ratio of the concentrations of the dissociated ions divided by the concentration of the undissociated acid. Then A minus and Ha are going to cancel out. And it means that this indicator must have an acid dissociation constant equal to the concentration of the H plus ion. And it means that it has a powers of dissociation constant pKa equal to the pH. Now let's take a look at how these graphs might look different. So in all four of these graphs right here, we've got an acid to start with and we're adding a base to it. So the pH is going up. But if we have a strong acid and a strong base, then what we find is that we get the full range. It starts off all the way down at 1, and adding more and more base would enable us to take the pH all the way up to 14. And it has an exceptionally long vertical section. It means that it's quite difficult to ascertain exactly where the middle is. If they were disbalanced, if we had a strong acid and a weak base, then what we find is that we could neutralize it at this equivalent point, but that we could never, no matter how much base we added, we could never ever cancel out the strong acid, and so the whole graph is skewed downwards, it's shifted downwards. And the opposite is true if we're adding a strong base to a weak acid. It starts off at a pH close to neutral and very rapidly will turn into a very high pH. If it is a weak acid and a weak base, then the curve, the vertical section is not very steep, it's more gradual, and the pH floats around 7, as we can see in these three graphs. So what those four graphs showed us was that the actual vertical section could exist, or the equivalent point could actually exist at different pHs. We don't always get neutralization at 7. We could get the neutralization of a strong acid and a weak base at a point in pH that was lower in number. It would be skewed downwards. So what we have to do is select an indicator that has a sensitivity range during the vertical section, and preferably in the middle of the vertical section of the particular acids and bases. You can see in this diagram here, phenolphthalein doesn't catch the equivalence point, and neither does methyl orange in this situation. But bromothymol blue does, and so that would be a very good choice of indicator. So again, just to find the indicator use, if we first look at the red line, the one that is at the bottom, the titration of the strong acid HCl, what we can see is it has this equivalence point at about 7, that the strong acid and the strong base have perfectly cancelled out at the midpoint of the pH scale, in the middle of the sensitivity of the litmus paper. So that would be a really, really good indicator for this. But the weak acid, this ethanoic acid that's at the top here, the CH3COOH, what we can see is it has an equivalence point higher up on the pH scale at about 8.72. So litmus would be a poor choice. We wouldn't catch the equivalent point, but phenolphthalein would.